Let's go over the sample test for Unit 4. Given the table of data where X is the month, so these are the months, 0 months, 1 month, 2 months, and Y is the number of cases in hundreds, determine the average percentage increase. And this could be cases of some disease, or it could be, we don't know. Anyway, so we're going to try to figure out the percentage increase on average. So we figure out the percentage increase here by finding how much it increased, which went, and what the formula was P2 minus P1 divided by P1. P2 minus P1. 18 minus 15, that's 3, divided by the beginning one, 15, which is, if I take out the calculator, I believe that is 1/5 or 0.2. 3 divided by 15 is 0.2. And from 18 to 22, that's 4 divided by 18. 4 divided by 18, that's 2/9, which is 0.22222. And so if I want the average percentage increase, I'm going to add these up and divide by 2. And so I get 0.4222 divided by 2, which is 0.2111. That's the average. Now, if I want it in percentage, it's 21.11% increase on average. I'll accept either form for this. So what's the exponential model? Okay, so we have the exponential model is the amount after some time is equal to the starting amount times 1 plus the interest rate, or the rate, to the t. Well, the rate is 0.211, so its starting amount was 15. So we have 15 times 1.21% more, so 1.211 to the t. And there's our model for how much there would be after some time t. How many months would it take to double the number of cases? So to double, this has to be 2. 2 times how much there was would be it. So we're trying to solve when 1.211 to the t equals 2, twice as much. Or you could say, when is 30 equal to 15 times this? And one way to do that is just to graph the two. Y equals, and clear, and put in 2, and then put in 1.211 to the x, and go, let's go zoom 4. There's one, and there's the other, and they cross at, let's see how many months it is when they match. So second, calculate the intersection of that one, and my guess is comes out, and it says it's 3.62 months. So not quite 4 months. You could say 4 months, but you could also just keep working this out, put in t equals 0, put in 1, put in 2, put in 3, put in 4, and you find out that 4 would be more than double and less would there. You could also rewrite this in logs. You could say, let's say we did it in base 10. 10 to the log 2 equals 10 to the log of 1.211 to the t, and then you could, since they have the same base, these would have to equal, and so you'd have log 2 equals t log 1.2111. And so if I divide log 2 by this, I'll find out what t is. So if I take log of 2 divided by log of 1.2111, close parenthesis, I should get the same, roughly the same number, 3.62 rounded off months. Okay? So now we got basically a similar problem. So we want to take what it was later, 0.71 minus what it was, 0.75 divided by the starting amount, 0.75. This will be minus 0.04 because it went down, went from 0.75 to 0.71, which is down 0.04, over the starting amount, 0.75, and that works out to be negative 0.04 divided by 0.75, and I get from here to here the decrease was 0.0533%. It went down by that much. In the next one, 0.71 to 0.68, that's down 0.3, down 0.03, divided by the starting amount, which was 0.71 there, and that comes out to be negative 0.04225 or 23, rounding it. And the next one, 6.8 to 6.4, that's down 0.04 divided by the starting one, 0.68. And we get negative 0.0588. And the next one, 6.4 to 6.1, that's down 3, down 0.03 divided by the starting one, 0.64, and that's negative 0.0469. And so to get the average of these, we would add all those up. They're all negative, so I'll just add them up and put a negative on my answer. So I'm going to say 0.0533 plus 0.0423 plus 0.0588 plus 0.0469, enter, and then divide that by 1, 2, 3, 4, and I get that the average is going down 0.0503, or going down by 5.03% on average. So what would be the exponential model? It would be 1 minus that much, minus 0.0503 to the t, starting amount 0.75 equals amount sometime later. Okay, so we have the model, an exponential model. It says write it in base e. So this number is, and we could have done that, that's 1 minus 0.0503, which is 0.9497. I could have written that to the t times 0.75, and if I'm going to write it with a base e, I just need to change that to base e, so it's 0.75 e to the natural log of 0.9497. that would be this number, to the t, which turns out to be 0.75 e to the ln of 0.9497. So I want to do ln of that last answer, and it's negative 0.516 t. ln of that is this. And so now we have it a base E model. And what is the half-life of this isotope? So this is something that's decaying. So the half-life, we just want to know when whatever we started with turns out to be half as much. So this part has to be a half. So 0.5 has to equal e to the negative 0.516 t. Or this has to be that. And whether I use this or this or this, they all have to equal a half. Half of the starting amount. Half of the starting amount. Half of the starting amount. So to solve this, I can write this in base E, which would be e to the ln 0.5 equals e to the negative 0.516 t. So ln 5 has to equal this. So I just have to divide, I'll write that. ln of 0.5 has to equal negative 0.516 t. So I divide both sides by negative 0.516, negative 0.516, getting rid of that. And so the t, the half-life, when it gets to be a half, is going to be that. So I'm going to type in ln 0.5, close parenthesis, divide by negative 0.516, and the half-life is 1.34, and x is in years. So t or x is years. Okay, page 2, number 3. So this looks like it has a base of 2. So this is 2 to the negative 1 times 2 squared to the 3x equals 2 to the x plus 1. So over here we get, multiply these, we get 6x, and then we have to, when we multiply, we add it, so we get 2 to the 6x minus 1 equals 2 to the x plus 1. Same base, so the powers must equal, so 6x minus 1 should equal x plus 1. Subtract 6 from both sides. Add 1 to both sides. And so x would equal 2 divided by 5, or 0.4. That's what 2/5 is in decimal. Now I can check my answer. We can go 1/2 times 4 to the 3 times 0.5. Oh, 0.4. And we get 2.639. And we can go 2 to the 0.4 plus 1, 2 to the 1.4. And notice we get the same number, exactly. Okay? Now this one, we're going to have to do approximations, and we can do this in any base. Base E, base 10, whatever you want to do. Base 5. It's easier to type in base E or base 10, so I'm going to write, I don't know, let's do E. E to the ln 5, that's another name for 5, times e to the ln 10 to the 2 minus x, equals e to the ln 7 to the x. So then this becomes 2 times the ln 10, 2 ln 10, yes, and minus x times ln 10. And we got to add to that because we're multiplying. We add plus ln 5 equals x times ln 7. Okay, now these ln's are just numbers, so we can just do, so this might be the easiest for you at this point to do. So ln 5 is 1.609 plus 2 ln 10. 2 ln 10 is 4.6605 minus ln 10 times x. ln 10 is 2.303, rounding that 2 to with the 5, x equals x ln 7. ln 7 is 1.946x. So I'm keeping 3 decimal places just to get a better answer. And this has an x and this has an x, this doesn't and this doesn't, so these can go together. So 1.609 plus 4.605, enter, is 6.214. And I'll add this amount to both sides, 2.303x, 2.303x, and I get 1.946 plus 2.303 is 4.249x, and to solve for x, I divide by the number that's times it. 4.249, and x equals 6.214 divided by 4.249 is 1.462 approximately. So that should be the number I can put in for x here to get that. Now I'm going to do what I've done before. I'm going to hit store and store my answer. So it's going to store this into x. So now if I type x, x is that number. And so I can just type this in 5 times 10 to the x, 2 minus x, 2 minus x, and see what that equals, and do 7 to the x and see what that equals, and you notice they're about the same. So that is a reasonable answer. Okay? Evaluate and get the exact values. So this says 3, and to what power do I take 1/5 to get 25? So to what power do I take 1/5, to what power, to get 25? Well, if I take it to the -1, I get 5. If I take it to the -2, 5 to the -2, that is would be 1/5 to the -2. The minus would flip it over and make it 5. The 2 would make it 25. And so the answer to this part, the 1/5 to the minus 2. And of course, you could just type that into your calculator. If you got math and you go down to log in a different base, you can type in the base of 1 divided by 5, and you can put in 25, and it says that's minus 2. Minus 2 times 3 is minus 6. You could actually type the whole thing in and get that. Now, if it came up with a decimal approximation, then you would have to do something else. What's this? Well, you could type this in, but pi is going to be not exact if you type it in. It won't give you an exact, it'll give you a decimal approximation. But e to the ln base e, just like we've been changing things like 5 to e to the ln of 5, e to the ln of pi over 3 is going to be pi over 3. It's like I changed this to e to some power. So that's what that one is. And this one says, to what power do I take this understood base 10 to get 10 to the 15th? Or I could take 15 down and say, it would say 15 to what power do I take 10 to get 10? And this is 1, so I get 15 times 1, which is 15. Those are exact values. This is exact. A decimal wouldn't cut it here. Okay? Now we've got to solve some equations. Okay, so it says subtract. I'm going to put the 2 up as a power, so I'm going to have log of x squared minus log of x minus 2.5 equals 1. And of course, these are understood base 10 because it doesn't give you a number. And when you subtract, you divide. So we're going to have log base 10 understood of x squared over x minus 2.5 equals 1. Then we're going to convert it using the power equation. Power to log, log to power, log to a power. This says, to what power do I take 10 to get this? I take 10 to the 1 to get this. So 10 to the 1 is 10 equals x squared over x minus 2.5. To solve this, I'm going to multiply both sides by x minus 2.5. These cancel out, and I get x squared equals 10 times this, which would be 10x minus 25. So subtract these both over because I got a quadratic, and I'll have 0 equals x squared minus 10x, subtracting 10x from both sides, and adding 25 to both sides, I get plus 25. And that factors to x minus 5 and x minus 5. Or you could graph this and it would just bounce off at 5. And so that says x has to be 5 if that works. You got to always check your answer. So if I put 5 in here, log of 5 I can do. If I put 5 in here, 5 minus 2.5 is positive, so I can do that. So that 5 should work, and so this is okay. If it didn't, there might not be any answer that make this work. But in this case, it does work. And you can check it on your calculator. You can go 2 log 5 minus log of 5 minus 2.5, close parenthesis, and I press enter, and I get 1. Okay, page 3, which is a continuation. We got to do this log one. Now this says plus, and if we're going to get to a single log, we do what this says. When it's adding, you multiply these, so you get log base 3 of x plus 4 times x minus 2 equals 3. And we can then write this as a power equation. So this would be x plus 4 times x minus 2 equals 3 to the 3, which is 27. 3 cubed is 27. So now to solve this, this is going to be a quadratic, and so we have to have it equal to 0. So we're going to have to multiply this out. X squared minus 2x plus 4x minus 8 equals 27. Subtract 27 from both sides, and you get x squared plus 2x minus 2x plus 4 is plus 2x. And minus 27 and minus 8 is minus 35 equals 0. And you could graph to find the answers. This one turns out to be factorable, and that's x and x. 35 is 5 and 7. So if we do plus 7 and minus 5, it says that x would have to be minus 7 or x would have to be 5. And minus 7 in here would be log of a negative, and you can't do that one, so that's an extraneous solution. Can we put 5? 5 plus 4 is positive 9. That works. 5 minus 2 is 3. That works. And so we could put that in there. And we could type this in. It's in base 3, so it's a little bit messy, but you can go ahead and type that in if you want. 5 does work. Okay, assume there's a radioactive isotope that decays according to this kind of formula. The amount after some time is equal to the amount you start with, e to some constant for this isotope, T. What is that constant? Well, determine the K if in 10 grams, starting with 10, ends up to be 2 grams in 12 years. So T is 12. We don't know the K. We got to find that. And 10 grams went to 2 grams. Starting amount ends up to being 2. So to solve this, we divide by 10, and we get 0.2 equals e to the 12k. 12 times k, 12k. So if we write this in same base, this would be e to the ln 0.2. So 12k has to be ln of 0.2. And we're going to divide by 12, and this would be the exact value for k. We can also get the approximate value by going ln 0.2 close parenthesis divided by 12, and it's the k approximately is negative 0.13412. So we found the K for this radioactive isotope. So now it says, what if you started with 50 grams? Okay, so we got a new starting amount, 50. E, the K is going to be the same because it's the same isotope, negative 0.13412 after 20 years times 20 equals the amount there would be left, and we're supposed to find out how much is left, the amount after that time, after 20. So all we have to do is type that in. 50 e to the negative 0.13412 times 20. And if you're doing it on a calculator that doesn't do exponents, you got to do shift it up. You have to put parentheses around your exponent. And this works out to be 3.42 grams. So the 50 grams decayed in 20 years down to 3.4 grams. In how many years will 10% still be radioactive? Well, it could be any amount. We could say 50, 10% of that would be 5. So we could put 5 here and 50 here. Or we could say this, no matter what the starting amount is, has to be 10%. So 0.10, 10% in decimal, would have to be e to the negative 0.13412 t, or x, or whatever. And we could graph that and graph that, find the intersection. Or we can write this in base e, which would be e to the ln of 0.10. So this would have to equal this. So to find t, I would just divide by this amount. So I have ln of 0.10 equals negative 0.13412 t. Divide by this, negative 0.13412, and divide this side by that, negative 0.13412, and that would tell me what t is. ln 0.10 divided by negative 0.13412, and that works out to be about 17.16 years, because the time was in years. And D, what's the half-life? So instead of just 10%, it would be 50%. So it'd be exactly the same process here, except I'd be put 0.50. So I can go back here and just put in 0.5, and I get, takes 5.168 years for it to be down to 50% of what it started to be. Page 4. And remember, I said in class that this is probably more than I would expect you to do in one class period. But there might be some of these that I won't do, but I'm just wanted to give you an idea what I could do. So here's an investment of $3,200 at 6%. How much is in the account after 10 years if compounded quarterly? So our compounded quarterly formula, which you have in your note card, is starting amount 1 plus interest rate, which was 0.06 is 6% in decimal, divided by how many times a year? Quarterly, that would be 4 times a year, to n, 4 times the number of years, which after 10 years, so 4 times 10. So that's 40. So I got to go, and the starting amount was 3,200. So I'm going to type in 3200 parenthesis 1 plus 0.06 divided by 4, close parenthesis, to 40. And after the 3,200 would increase to $5,804.86 rounded off. How long would it take for the balance to grow to 4,000 if compounded quarterly? So now, instead of putting 10 years here, we're going to put an X or a T, and we're going to put the 4,000 there. So we got 4,000 equals 3,200 times 1 plus 0.06 divided by 4 to the 4 times t. Now, to make this a little simpler, we could divide both sides by 3,200. So we don't have such big numbers. And so we're saying, when will the account grow to be 4,000 divided by 3,200, grow to be 1 quarter times as much as it was. So we've got 1.25 equals 1 plus 0.06 over 4 to the 4t. I'll do this one by graphing just to remind you that you can do this. I'm going to go to y equals and type in 1.25, and I'm going to type in parenthesis. Let's clear this and do parenthesis 1 plus 0.06 divided by 4, close parenthesis, to the 4x. And I'm going to go zoom 4. There's one, and there's the other, and they cross right about 1, 2, 3, about 4 years, a little less than 4 years. Let's see what it is. Second, calculate the intersection, or just tap on it if you're doing Desmos. Enter, enter, and enter. Oop. Oh, messed it up. Second, calculate the intersection. Enter, enter, enter. And it tells me T would be 3.75 years. It would grow from 3,200 to 4,000 in 3 3/4 years. That probably sounds like a lifetime for a college student. How long would it long for the balance to double if it was compounded? Okay, so this would have to be 2 to make this be 3,200 to 6,400. You could write 6,400 and divide it by 3,200, but you would get 2. This has to be 2 times this. So you can just write 2 equals 1.1 plus 0.06 over 4 to the 4t. And we could solve it the same way we did before. We just put 2 here instead of what's there. And we graph. There's the 2. And it looks like we're having to go further over here, so I'm going to go to my window and look for bigger x's, like maybe 20. See if it's within 20 years do they intersect. And they do, somewhere around 12 it looks like. Second, calculate the intersection, that graph, and the intersection, and it says at 11.64 years, approximately. And last one. How much is in the count in 10 years if compounded continuously? So this is a new formula. Continuously, A of t is the starting amount, 3,200, e to the interest rate in decimal, so 0.06 t, and if this is in 10 years, so times 10. Starting amount, e to the rate times the time. And so it should be more than it was for 10 years here. Compounded continuously, grows a little bit faster. Not much more, but a little bit. So we're going to do 3,200 e to the 0.06 times 10. And that comes out to be $5,830.78, which is about 26 bucks more than up there. Okay,